This video gives a brief introduction to our work published in IEEE Transactions on CSVT in 2018. The title of this paper is Learning Affective Features with a Hybrid Deep Model for Audio-Visual Emotion Recognition. This is a joint work by Shiqing Zhang, Shiliang Zhang, Tiejun Huang, Wen Gao, and Qi Tian. This paper is related to affective computing. This is a very important topic in CSVT community. It tries to sense human affective responses and apply affective cues to help computing, communication, and other applications like human-computer interaction, media analysis, and brain science. Well, the focus of this paper is audio-visual emotion recognition. Well, the general pipeline is that given an input video sequence including both audio and visual signals, we extract audio features and video features respectively. Well, then fuse those two modalities and recognize the emotions. Well, the most important steps are feature extraction and multimodality fusion. For the feature extraction, most of previous works use handcrafted features like audio features, video features, and they suffer from the gap between low-level handcrafted features and high-level emotions. For the other step, the multimodality fusion, there are many well-known fusion models like feature-level fusion, decision-level fusion, score-level fusion, and model-level fusion. Well, but they exhibit limited capability in modeling complicated nonlinear correlations of multiple inputs. Well, in recent years, deep learning has become the mainstream method in visual recognition. Well, deep learning has shown very interesting properties. Well, the first property is hierarchical feature learning capability. It learns discriminative hierarchical features in an end-to-end training. Well, the learned features are better suited to depict high-level emotions than handcrafted features. Well, the other property is the deep model. The deep model presents very good discriminative power in modeling semantic concepts and could be better suited to model nonlinear correlations among multimodalities. However, deep learning has not been fully explored in emotion recognition before this work. Therefore, our motivation is quite clear. So we try to learn audio and video features with CNN respectively, then fuse audio and video features with deep models to recognize emotions. Well, this shows the framework of our proposed hybrid deep model. So given an input video, we break it into different segments with equal lengths. For each segment, the audio signals is converted into a 2D representation and feed into a 2D CNN for audio feature extraction. While the video frames are inputted into a 3D CNN for video feature extraction. So the audio and video features are then fused by a deep belief network, the DBN, to learn the fused feature. So finally, pooling is applied on features of different segments for emotion recognition. Well, so the most important steps are audio feature extraction, visual feature extraction, and feature fusion. Well, this is the pipeline of audio feature extraction. Because most of CNNs use 2D representations as the input, so we first convert audio signal into a 2D representation to leverage the latest advances on deep learning. So this is achieved by computing the Mel spectrogram on each audio segment to get a 2D matrix. So we compute the first and the second order Mel spectrogram, and finally could get a RGB-like 3-channel representation. So we then resize it and input it into XNet, which is pre-trained on the ImageNet dataset. And we finally fine-tune the XNet on emotion recognition task and use the output of FC7 layer as the audio feature. Well, the extraction of a visual feature is achieved with a visual network. So we first produce video segments with 16 consecutive frames, then feed each video segment into a 3D CNN. So in this task, we use C3D-CNN pre-trained on a sports video dataset as a 3D-CNN model. We finally fine-tuned the 3D-CNN on emotion recognition task and used the output of FC7 layer as the visual feature. The extracted audio and video features are fused by the fusion network for emotion recognition. So we use the deep belief network for feature fusion. The DBN outputs the joint feature representation for each segment. After getting features of all segments, we apply average pooling on those features and adopt classifiers like linear SVM to perform the emotion recognition. The proposed method is straightforward and easy to repeat. The training of the hybrid deep model mainly contains two steps. We first train the audio and the video network. For instance, we minimize the emotion classification error to optimize the audio network and audio features with backpropagation. The video network and the video features are optimized with a similar strategy. Based on the optimized video and audio features, we then train the DBN network. This is achieved with two steps. We first use the unsupervised pre-training to minimize the reconstruction error between its input and the reconstructed output. We then use the supervised fine-tuning to optimize DBN and diffuse the feature with backpropagation. For the experiments, we use 3 emotion recognition datasets and follow their settings. Those 3 datasets contain 6 emotion labels: anger, joy, sadness, surprise, fear, and disgust. The RML and interface 05 datasets contain active emotions, and the other BAUM1S contains spontaneous emotions. Therefore, the BAUM could be more challenging. First, test the performance of our feature learning model and the learned features. We first show the performance of pre-trained CNN models. The LX audio denotes the LXNet pre-trained on ImageNet, and the C3D video is pre-trained on the sports video dataset. It is very interesting to observe that those pre-trained CNNs get reasonably good performance. It's also clear that fine-tuning on emotion recognition tasks significantly boosts its performance. We further compare our features with previous ones, and it's clear that our features perform significantly better than previous handcrafted features. Next, we test the performance of our feature fusion models. We compare with many well-known fusion models like feature-level fusion, decision-level fusion, and score-level fusion. It's clear that our DBN gets better performance. We also compare with FC layers with similar structure. It's clear that our DBN performs better than FC layers, and it's also can be observed that DBN with 4 layers get the best performance on 3 datasets. Well, this page shows our comparison with previous methods on 3 datasets. This is the final result achieved by fusing both audio and video features. We can observe that combining audio and video features, our method gets very competitive performance and outperform those state-of-the-art ones. The following figures show the confusion matrix on 3 datasets. On the first 2 datasets, our method achieved quite reliable classification results. For the BAUM1S dataset, it's more challenging because it contains spontaneous emotions. Well, this page shows some emotion recognition results by our method and the previous one. It's clear that our method gets better results. We can summarize our contributions into 3 aspects. This is an early hybrid deep model for audio-video emotion recognition, and it significantly outperforms previous works relying on handcrafted features. This work effectively transforms 1D audio signal into a 2D representation, and it benefits emotion recognition with recent advances on visual recognition. We also demonstrate that CNN pre-trained on other image and video datasets work reasonably well on emotion recognition tasks. Well, the future work can be conducted to explore more efficient end-to-end training strategy, build lightweight hybrid model, and explore better pooling strategies. Thanks for your attention. For more detail about this work, you can refer to our work paper and this link.